Assalamu alaikum student. This is the video number 1 of week number 13. As you know, we have already covered the content of the course, and this is basically is the revision of the course, and I am focusing the topic that in which I did not solve the practical problem, too many practical problems. So here I'm trying to elaborate those topics which I feel need to be discussed more in detail, which will help you in the forthcoming course FM2. Okay, and these topics will basically make your foundation, okay, to carry out those courses. So today the topic I have chosen is the from the chapter finite control volume analysis. Okay, and in this chapter the topic we are going to cover today are basically the conservation of linear momentum. Okay, that we have already previously discussed, and we will do many practice problems from it. Okay, so the conservation of momentum basically, when we in FM2, basically we will discuss in detail the turbo machinery. Okay, so here in fluid mechanics, okay, we are discussing the effect of how the linear momentum come into picture when the fluid act like a jet or whenever the fluid passes through a bend of any angle, the pipe bends, I mean. Okay, so whenever the fluid passes through a pipe bend, okay, whether it is a open channel or is the closed pipe, okay, so always it comes into picture. So we are going to discuss here that uh, here what is a turbo machinery and how we utilize uh, the phenomena of linear momentum, okay, to achieve our objective. So here, first of all, we see what exactly the turbo machinery is and how these machines how these machine operates by using the phenomena of linear momentum. So here in turbo machineries, either we applied force on the fluid uh, by the machine or by the object or by the solid object, or the fluid exert a force on the solid object. As you can see, we have the example is the turbines and the pumps, the compressor. In turbine, basically we use water jets, okay, the fluid water jets. The fluid may be a gas, okay, maybe water or maybe any other liquid, okay. But but commonly we use water, okay, or steam of water, okay, to operate the turbines. Okay, so here you can see the example of, here you can see a picture. Let me highlight for you. So this is basically the jet, okay, and this is basically jet you can see. So here the water jet is basically exerting force on a on a rotating wheel, okay. So because of the change in momentum, okay, the wheel rotates. And in the pump or in the compressor, so by using the impeller or by using the piston, okay, we compresses the fluid or we push the fluid, okay, by using the impeller or the blade or the pistons, okay. So let's see what is exactly the turbo machinery. The turbo machineries in mechanical engineering here describes machines that transfer energy between a rotor and a fluid, okay, including both turbine and compressor. So as I explained to you in turbine, basically the blades the water jets, the fluid exert a force on the solid object, okay? And in compressor or in pump, okay, in compressor and in pump, basically the solid object or the machine exerts the force on the water or on the fluid, whatever, because as we all know that the compressor we are using to compress gases, okay, and the pumps we are using to transfer liquid from one point to another point or to pressurize the liquid to a required level. Okay, so while a turbine transfers energy from a fluid to a rotor, okay, in turbine, the fluid transfers its energy to rotor. A compressor transfers energy from a rotor to a fluid, okay, as I just said. So just we are seeing that uh, how this phenomena uh, happens or how do we calculate the effect of uh, momentum, okay. So according to the second law of Newton, okay, we know that force is equals to ma and m is equals to v1 minus v2 into t. So as we know that the acceleration is basically the change in velocity. So this is the change in velocity, okay. So rate of change of velocity is equals to acceleration, okay. So we all know that acceleration is equals to rate of change of acceleration, okay, rate of change of velocity. So this is basically the rate of change, you can see rate of rate of change rate of change. So you can, it's hard to write basically. So rate of, sorry about that, rate of change of velocity. Okay. So here same, the rate of change of velocity is equals to acceleration. Okay. So from here, there is a concept of impulse arises. Okay. So what is basically the impulse? So whenever an object, okay, uh, whether it is in rest or whether it is moving, whenever the two objects come in contact for a small period of time, okay, so basically the impulse occurs, no? Because whenever those two objects are come in contact, okay, if it is stationary and other is moving, so when they come in contact with each other, what exactly they do? They transfers their energy from one body to another body, just like a stick of a golf and the ball. Okay, whenever you hit a stationary ball with a stick, what happens for a very small period of time? So what happens? The moving sticks transfers its energy to the stationary ball. So same here, okay, when the just like cricket ball and the bat, the football and the kick. Okay, these all are the example of the impulse. So same here, if you can define impulse of a force is given by the change in momentum caused by the force on the body. Okay, so this is basically the impulse of a force. So it is a force given by the change in momentum caused by the force. Okay, so whenever we apply a force, so because of that there is a change in momentum of the in the object. Okay, that also we can write down. So here you can see the force. So take this t here, so this will become ft and this will become mv1 minus mv2, initial minus final. So here you can see that this is basically what? This is basically the impulse, okay? And this is change in momentum, okay? So that's why we can say that, okay, the impulse is equals to change in momentum, okay? Or we can say that, K force, the net force acting on an object is equal to rate of change of momentum. Okay, the rate of change of momentum. So if you can take it t down, so what will happen? The net force will be equal to rate of change of momentum. Okay, so here the impulse is equals to change in momentum, but the net force, according to the second law of Newton, the net force is equal to rate of change of momentum. And here you see force exerted by the jet. So first, so here we are going to analyze two things. The force exerted by the jet on the object, okay, the fluid jet. We are talking about the fluid jet, okay, whether it is water jet or whether it is a steam jet, okay, on the object. And second, the fluid flowing through the pipe bends or through the pipe, okay. So the pipe bends or the pipes, if the pipe sizes is changing, so what happens? There is also a change in momentum, especially we see in the fire hydrants, fire tenders, bowser or the nozzles they uses uh, they uses to suppress the fire. And we see the phenomena of change in momentum also in the when the pipe size changes, especially in the sprinkler of garden sprinklers. Okay, so these phenomena are basically happens because of the change in momentum. So here you can see, so this is basically the impulse, okay, and this is change in momentum, okay. So here the force exerted by jet on the plate in the direction of jet. So I will talk later about this plate and the concept of plate. Okay, so just consider that the same equation continues. Okay, so here what we are saying, the force exerted by jet. That means the force exerted by fluid, and this happens. Okay, in the garden sprinklers, in the basically in turbines, in whenever you reduces the pipe sizes. Okay, so the force exerted by jet, this jet. So the difference between the jet, what is the jet? Whenever uh, uh, whenever the fluid, okay, travels in an open atmosphere, okay, there is no pressure change, okay. In the jet the water flows through a very high velocity, okay, uh, when there is no pressure change, okay, in atmosphere, that p1 minus p2 is basically the zero. The change in pressure is zero. The pressure is atmospheric pressure or maybe, but there is no change in pressure, okay. So in the direction of jet, okay, plate in the direction of jet, so F is equals to the same equations that we put it here, okay. So here you see this is mass, Mass over time is what? The rate of change of mass is equal to kilogram per second. That will give you mass flow rate. Okay, that will give you mass flow rate. M dot, and M dot is equals to, you know that M dot is equals to rho AV, that is rho A, and this is V, density time area into velocity. So here you know that A into V is equals to flow of jet. So this is your Q. Okay, so this what we have written here, कि mass over time, okay, is equals to rho into Q, or rho AV into initial velocity minus final velocity. So this exactly we have done in this equation. Okay, so when to use this equation we are going to discuss further. So let's see here, the force exerted by the jet. So basically, the application of jet is mainly in the turbine, okay, where we rotate the turbine wheels by using a very strong jets, okay. So the wheels are basically how we are discussing now. Basically, in the wheels we use different types of blades. Okay, the blades, and we strike the jet with the different angles. Okay, just like you see here, the jet is straight. Okay, jet is straight. So jet, maybe we can strike like this with a some certain angle. Okay, some here, just like I can make a jet like this also. Okay, or I can make a jet. We can apply with a different angle to increase the efficiency of the turbine. Okay, or to uh, consume the energy from the fluid. Okay, so here you see, because of that we are trying different type and shapes of blades. Here you can see the blades are straight. Here you can see in this wheel the blades are circle. Okay, and also this is one thing, right? Okay, we are changing the blades, we are changing the shape or structure of the blades, and the other thing that we can change, the direction of the jets. Okay, so there are two ways that basically we are going to discuss here, and we will handle both the situation, okay, when the type of the blade changes and when the angle or direction of the jet changes, then how we basically solve those problems practically, okay, or numerically. Right. So here you see, we can see here the force exerted by the jet. The first condition we are considering, the flat, the force exerted by the jet on a stationary plates. Okay. So when the plates are stationary, and second, the force exerted by the jet on a moving plate. The first case, when it is moving with a particular velocity, and the second case, it is stationary. So in case of stationary, plate is vertical to the jet, just like this is vertical to the jet, and this is also vertical to the jet. Okay, the plate is inclined to the jet. So this is plate is inclined to the jet. Okay, this is straight, this is inclined, and plate is curved. Okay, the plate is curved. Okay, inclined means, so this is inclined. Okay, so either you can strike this, okay, or you can make certain angle from here. Okay, you can make certain angle from here. So this is the example of a flat plate, and this is the example of curved plate. So in the second part, the force exerted by the jet on a moving plate. So when the plate is moving with a particular velocity u, when the blade is moving with a particular velocity U. Okay, so either this way or this way, the blade can move either in the direction of the jet or opposite to the jet. Okay, in both the cases, please listen carefully. The blade may move in the direction of the jet. So this is the direction of the jet. Okay, and if the blade is moving in the same direction, in the same direction, just like this is the direction, the blade moving in this direction. Same here, you can see, same in the case of curved blade, okay. Uh, if it may move in the direction of jet or it may move, this is the, basically if the direction, if the jet is in this direction and it is moving in this direction with the velocity u, okay, or it may move in the opposite direction also. So what would be the case? Okay, if the v, the velocity of jet, okay, and the velocity of the blade is in same direction, and the velocity of jet and velocity of the blade is in the opposite direction. So let's go and analyze one by one. So and how we can calculate those forces or energy or the work done or the efficiency of the machine. Let's see. The force exerted by the jet. So here are basically the three conditions that basically we are going to focus here. Okay. The first, in the first case, you can see here, we have taken a flat plate. So this is all flat plates, okay? And there are two possibilities that we have previously discussed. In the first case, the blade is stationary, and then the second case, the blade is moving with a certain velocity. So here you see this is a vertical flat plate and the fluid jet is perpendicular to the plate, okay, and then water discharges tangential to the plate, okay, parallel to the plate. Okay, so in case if the plate is stationary, okay, so directly you can use this equation and you can solve your problems if you can. Okay, in case if the plate is stationary, okay, and the fluid jet is striking on it, so this is the equation that you can use it to solve the problem. Okay, so because you see this is the force exerted by the jet, this is F, okay, and because you see there is no change in momentum, okay, so there is a, this is what, this is our rho into A into V square. So the change in momentum, you see how we can do that, rho into A is same into velocity of the jet, okay, multiplied by v minus u, okay, v1 minus, sorry, v1 minus v2. So this is v1, this is v1, and this is v2. So since if you consider this is the velocity of the jet, so don't put any v, don't put any v, okay, just to verify this equation. And this consider you velocity, we consider v2, okay. So here you can see the jet area, this is the area of the jet, the cross-section area you can take. If the diameter is given or the area is given, you can take it straight away. And rho is the density of water. So you can determine this property if the temperature is given, okay. And also if temperature is not given, so you can take the standard value that we all know, okay. And since the jet is moving in the x direction, so if this is the x direction, okay, or the horizontal direction, and this is the y direction, or the net force, okay, so net force acting in the z direction, okay, and net momentum acting in the net momentum in the z direction. So this is the direction of jet. Okay, so here you can see the velocity in the jet direction initially is v. Okay, the initial velocity in the jet direction is v. So we have taken v here. Okay, and the initial velocity is v. So what is the final velocity in the jet direction? So in this direction there is no velocity. Okay, so here we can say v2 is equals to 0. There is no velocity in the z direction. So that is why we consider this vector 0, okay, and this value become rho. So this v and v become v square. So rho a v square. Okay. Now in the second case, if the plate is moving, okay, if the plate is moving, so basically what will happen, there will be a concept of relative velocity, or there will be a concept of approach velocity. Okay, so this I will discuss in more detail. So just consider if the plate is moving, okay, so this is the formula that we can use it. Okay, so if the plate is inclined, okay, if the plate is inclined, so we can calculate the force exerted by the jet on the inclined plate. So in the inclined plate, this is basically the normal direction to the plate. So this is the normal N. Okay, this is the, you see here, you can see here Fn. Okay, so Fn will be equal to rho a v squared sine theta in case of when the plate is stationary. Okay, when the plate is stationary, you can take it va sine theta. It's very simple. We can see here. So, if we want to calculate the force exerted by the jet in the direction normal to the plate, so we can see the jet is basically striking with some angle on the plate, okay, which is theta. Okay, so this is what? This is the axis of jet. This is the axis of jet. Okay, and this is the axis normal to the plate. Okay, so if you want to a force exerted by a fluid normal to the plate, so this is the direction and this is the direction of the force. So what would be the magnitude of the force? Okay, the formula is same. You see, the formula is same, but only thing, the velocity is not 100% perpendicular to the jet. Okay, so this is only we are using some component or some part of the velocity which is basically producing force normal to the jet. But in this case, the 100% velocity basically playing a role to uh, uh, to produce a force on the plate. Okay, so here just resolve if this is x and this is the line parallel to the plate. Okay, all right. So this is your 90 degree. Okay, this is 90 degree. So if this is theta, because if the jet is making some angle with this, okay, so what would be the what would be the corresponding angle? This is going to be, because you see this line I am saying and this line are perpendicular to each other. So this all is 90 degree. Okay. And this angle is theta degree. So this is theta. So this will become 90 minus theta. Okay. So this will become 90 minus theta. So what would be this angle? This angle will be theta. Okay. So if this is vector v. So if this is v, so what would be this component? Would be this component which is normal to the plate, that is v sine theta. So this will become v sine theta. So only v sine theta will contribute to produce a force on the plate normal to the plate. Okay, so that is basically rho v squared sine theta. And then similarly, we can take the component in x direction and y direction. So Fn, all right, so Fn sine theta in the x direction. So this is x direction, and this is, you can write down the component of normal force. If you can take in, if this is your x direction, so if you make the component from here, okay, if this is the 90-degree in x direction, okay, so this is basically 90-degree and this is your 90 minus theta. So fx will be f sine theta and fy will be f cos theta. Sorry. So this will become this will become, sorry, uh, let me clear. So this will be fx, okay, and this will be fy. Because you see here, if this is 90 minus theta, so this will be theta, okay, and this is basically the base, okay. So the y component, this is basically the y component, okay. The y component will be f sine theta and x component will be cos theta, okay. So same here again, if the plate is moving with an angle, if the plate is moving, okay, with the angle theta. So what would be the difference? We can replace this velocity v with the approach velocity or with the relative velocity. So what is the relative velocity? So whatever is the velocity of the jet and whatever is the velocity of the plate, so be, so relative velocity will be equal to v minus u. So with this difference of velocity, the jet will approach to the wheel. Okay. So let's close this lecture here. Inshallah, in the next lecture, I will explain this topic further.